Okay, so hi. My name is Shmarya Rubenstein. I'm a reverse engineer and hacker with more than 12 years of experience hacking on stuff in a professional capacity. I've spent a lot of time working on all kinds of systems, focusing primarily on testing of the security of embedded devices from the silicon and PCB layers all the way up through the firmware and software which actually makes things work. And I'm currently a researcher at NSO in Israel. Now, I'm not here to talk about NSO, although a lot of people are interested in NSO. But I would like to take this opportunity to say a few words about it and why I love working there. NSO's mission is to make the world a better, safer place by providing duly authorized law enforcement and intelligence agencies with the technical capability to lawfully gather intelligence and evidence which will assist in the combat of crime and terror. Not many companies can say that their goal is to make the world a better place. I love being able to face the really difficult challenges, technical challenges that we do in building stable real-world exploits while impacting the world for the better. But that's enough about NSO. Let's talk about what we're going to talk about today. What we're going to do is we're going to do a deep dive into the two libc allocators that are used on Android. And then we'll follow that up with some thoughts on exploitation and how you exploit heap buffer overflows, use after freeze, etc. On those various allocators. So all of the information that I'll impart is the result of our own research into the allocators in question, including a thorough code review of both of the implementations. That said, much of the information is available online in one form or another, but I've yet to encounter a concise but in-depth description of both allocators and hopefully and relevant exploitation techniques, and hopefully that's what this presentation will provide. I'm hoping to provide a reference on these allocators. So it's 2018, the days of trivially exploitable stack buffer overflows are over. Modern exploitable vulnerabilities fall into a few meager classes. Some of those we've heard from the previous presentations. We'll focus on two of these classes. Even at this late stage in the game, memory corruption bugs are still a thing, believe it or not. Chief among these is the good old buffer overflow. Stack cookies have largely neutered the exploitability of stack-based memory corruptions, so most modern memory corruption vulns are in objects and buffers that are on the heap, as opposed to the stack. In addition to these heap-based memory corruption vulnerabilities, we also have use after free vulnerabilities. This class of bugs is all about heap objects coupled with bad memory management practices. Together, these two classes make up a very large portion of the exploitable bugs that we find in modern software. What these classes of bugs have in common is that they both occur mostly in heap objects. Understanding how the heap works is a critical but often overlooked step in crafting reliable exploits for these kinds of vulns. Even if you look at the previous presentations, there was a little bit of talking about heap shaping, but the details of how you do that is a bit of a mystery still. When we talk about the heap, what we actually mean is any and all memory objects which are managed using the libc malloc free interface. This very simple interface lets us allocate so-called dynamic memory for our use, and then we free it when we're done using it. When we approach the task of exploiting a heap overflow or a use after free, it's not enough to know the semantics of this interface. We need to know what is happening under the hood. Android uses its own libc implementation called Bionic. When the Android developers came to implement these heap functions, they wisely chose to use an existing battle-tested implementation instead of rolling their own. The dynamic memory allocator implementation that they chose is called dlmalloc. It's named after its author, Doug Lee. Doug started writing this allocator way back in 1987. It has received many updates and improvements over the years and was last updated in around 2012. When you call malloc, dlmalloc does a bunch of stuff behind the scenes and will eventually return a pointer to a block of contiguous memory which you can use in your program. This block is called a chunk and is guaranteed to be at least as big as the size you requested. These chunks don't come from nowhere. When dlmalloc needs memory to use for chunks, it requests an allocation from the operating system. Each such system allocation is called a segment. Segments are the base unit of allocation from the OS. dlmalloc keeps a linked list of segments that is allocated from the system with the pointers stored in the segment's footers. The most recently allocated segment is the current segment. When it needs more system memory, dlmalloc first tries to extend the current segment using the sbreak syscall and falls back to mapping a new segment if that doesn't work. Segments can be of different sizes, but are always a multiple of the page size. Segments are not guaranteed to be adjacent to one another in memory, and in fact are allocated at random addresses when ASLR address space layout randomization is used, as it is on Android. If a new segment happens to be contiguous to an existing segment, the two segments are consolidated into a single larger segment, which is then dealt with as a single segment. The current segment contains the top chunk, which is the chunk of free space available for immediate allocation of chunks. Here's an example current segment with in-use chunks in green and free chunks in blue. You can see that there's some free and used chunks on the left there, on the right there. And then there's the big top chunk, which is the free space available in the segment. When dlmalloc needs to allocate a new chunk for a malloc call, it will check if the top chunk is big enough to contain the new chunk, and if so, it will carve the new chunk from within the top chunk by splitting it. The first half of the top chunk becomes the new chunk to be returned, and the second half becomes the new top chunk. If the top chunk is not large enough to contain the new chunk, a new segment is allocated from the operating system, and the new chunk is allocated from that new segment. Each chunk has 2 pointers worth of metadata. The 32-bit processors, this is 8 bytes, and 64-bit processors, obviously, it's 16. This metadata sits directly before the pointer returned by malloc, i.e. it's inline before the usable memory. The minimum amount of actual usable memory returned by malloc is 2 pointers wide. Chunks of different sizes can be allocated one after another in the segments. Each chunk marks its size and whether it is in use or not via the C in use flag. It also marks whether the previous chunk is in use with the P in use flag and the previous chunk size. Because the previous chunk size appears in the metadata for this chunk, we can easily walk backwards through the chunks to see exactly what exists in the segments. When you call free on a given chunk, the first thing that happens is that dlmalloc checks to see if the preceding chunk is in use. If the preceding chunk is free, dlmalloc will consolidate the two chunks into one larger free chunk. This means that it's impossible for two consecutive chunks in a segment to both be free. The chunks immediately before and after any free chunk are both guaranteed to be in use. Simple, right? Obviously, what we've described is a pretty naive allocator implementation. There's a little bit more to it. Specifically, what we've described is a system which never reuses freed memory, as it always allocates from the top chunk. So how do we efficiently reuse freed memory? We need some bins. Bins are used to keep a record of recently freed chunks which can be reused. There are two types of bins, small and tree. Small bins are used for chunks smaller than 100 hex bytes. Each small bin contains chunks of the same size. Tree bins are used for larger chunk sizes and contain chunks of a given range of sizes. Small bins are implemented as simple doubly linked lists, and tree bins are implemented as bitwise digital trees keyed on chunk size. There are 32 small bins and 32 tree bins, so there's already a large number of bins, 64 bins in the system. When a chunk is freed, it undergoes consolidation if needed, and then a consolidated chunk is added to the appropriate bin for its size. The list and tree node pointers are stored within the actual chunk data, which is safe to use because for metadata because this is a free region, free chunk. This is where the minimum size for a chunk comes from. We need space for the previous and next pointers in that free chunk's data. Here's an example showing a few segments with some in-use and free chunks. The 0x18 bin points to the first of the free chunks of size 0x18, and the rest of them are chained together in a doubly linked list. Note that the small bins contain chunks of exactly one size. Tree bins contain ranges of chunk sizes. dlmalloc is a best fit allocator. It will always try to find the free chunk with the smallest size greater or equal to the request size. During allocation, before looking at the top chunk, dlmalloc will first try to find a free chunk in the bins. It first tries to find a chunk which matches the exact size of the allocation request, and then moves upward through the non-empty bins till it finds the smallest chunk which is larger than the request size. If a larger chunk is used, it will be split, and the remainder will be added to the relevant bin to possibly be used for future allocations. Only if no chunk exists in the bins to satisfy the allocation request will the top chunk be used. Note that bins are first in, first out, so chunks are allocated in the order that they are freed. This can be a really important factor in exploitation, especially when you're doing multiple frees and allocations and trying to get things lined up as you want them to be. It's important to remember that the allocations will occur in the order that they were freed. After looking in the bins for an exact size match, but before going to the top chunk, there is another specific object called designated victim, which is then checked to see if it is large enough to contain the allocation request. The designated victim is the preferred chunk for servicing small requests that don't have an exact fit. If the chunk which was most recently, it's the chunk which was most recently split off of. It doesn't sit in any bin, and having the designated victim helps to localize allocations to a given memory segment, which can be useful when you consider how CPU caches work. Small allocations which don't have an exact size, an exact match in the bins will be split off from this chunk. So for a small allocation, a request size smaller than 100 hex bytes, this is the flow. We first calculate the exact size, including metadata and padding. We then look for an exact match in the small bins. If that fails, we next see if the designated victim is large enough to allocate from. If the designated victim is too small, we then look for a best fit in the small bins larger than our request size. If that fails, we look in the tree bins for a best fit match. And finally, if all else has failed, we look at the top chunk, potentially causing more memory to be allocated from the system. Larger allocations are a little simpler. We just try to allocate from the tree bins before attempting the designated victim and then the top chunk. There are no bins for so-called very large allocations, which means anything larger than the mmap threshold, which is 64 kilobytes on Android. These allocations don't come from the segments. Instead, each allocation is mmapped directly. That's dlmalloc in a nutshell. Hopefully I've covered all of the salient points, but there are a couple of things that we should note before we continue onwards. While dlmalloc takes some steps to reduce fragmentation of the heap, particularly the reuse of free chunks based on bin size, it is still common for smaller free chunks to get trapped between larger objects which tend to have a longer lifetime in application flow. dlmalloc is not thread safe at all. Both malloc and free touch process global data structures and the inline metadata between chunks and inside free chunks. Remember that dlmalloc was designed long before the age of parallelism, before every application was multi-threaded, before hyper-threading and multi-core processors. To make dlmalloc usable in a multi-threaded processes, Doug Lee chose the simplest possible fix, the big lock. Every single malloc of free call locks a global mutex on entry and unlocks it at function exit. This makes dlmalloc usable with threads, but has a major performance impact. Essentially, all allocator operations are serialized. This is okay on lightly multi-threaded processes, but can be a significant drag on more complex applications. The poor multi-threading performance of dlmalloc is one of the main reasons that the Bionic developers decided to switch to a more modern heap implementation. The new allocator selected by the Bionic developers is called JEmalloc. It's named after its implementer, Jason Evans. Jason started implementing JEmalloc in 2005. It was then added to FreeBSD's libc to become that platform's default allocator and remains so to today. In 2007, the Firefox Mozilla project, or the Mozilla Firefox project, adopted the standalone version of JEmalloc as their primary allocator. And since 2009, JEmalloc has been used extensively in Facebook's back-end servers, and it's currently maintained by a team of developers at Facebook. During May 2014, JEmalloc was added to the Bionic source tree for Android 5.0. dlmalloc continued to be the default, but it was possible to select this new heap implementation using a board config flag. In July 2014, JEmalloc was made the default. Now, in an ideal world, every vendor of an Android phone would have made the transition to JMalloc with their Android 5.0 ROMs. Unfortunately, many vendors chose to remain with the tried and tested DLmalloc heap until later versions of Android. In fact, I've seen DLmalloc being used in both Lollipop and Marshmallow devices. The fact that there is no clear line in time, clear line in the sand separating the two implementations means that you cannot really know a priori whether a given Android 5 or 6 device is using DLmalloc or JMalloc, which obviously makes exploiting it much more difficult. JMalloc was designed from the ground up to be highly performant in symmetric multiprocessing environments. It has many features which are geared towards increasing efficiency and locality in multi-threaded applications while reducing overall fragmentation. The first important concept in JMalloc's implementation is the arena. Each thread is assigned to a given arena on its first malloc, and it allocates and frees only from that arena. Each arena is completely separate from other arenas, and most importantly, they have separate mutexes guarding their data structures. This means that you can actually perform allocator operations in parallel so long as the threads involved are assigned to different arenas. In general JMalloc usage, there should be slightly more arenas than there are hardware cores. For some reason on Android, this is not the case. Instead, we have exactly 2 arenas. Threads are assigned to arenas in a round-robin fashion, which should ensure that the arenas have a more or less equal number of threads. In JMalloc, memory is allocated from the operating system using mmap. Each mmap operation allocates a chunk. JMalloc chunks are roughly correlate to DLmalloc segments. Chunks are all the same size, 256 kilobytes on Android versions up to 7.0. From 7.0, chunks are 512 kilobytes for 32-bit processors and 2 megabytes for 64-bit processors. Each chunk belongs to a specific arena. There is a chunk header containing metadata for this chunk, specifically including a page map which defines which pages are associated with which runs. We'll talk more about runs in a moment. For any JMalloc managed address, the relevant chunk header can easily be found by simply rounding down the address to the chunk size. This means that we have O of 1 lookups of metadata in most situations. A run is an area of contiguous memory located in a chunk. Each run contains a fixed number of regions of a specific size. Different size classes have different numbers of regions. Runs are always a multiple of the page size, and run metadata is stored in the chunk header for the chunk which contains them. In other words, the metadata is out of band. Each run has a bitmap which indicates the state of each region in the run. A region can either be in use or free, setting or freeing that bit. Regions are the smallest units of allocation in the JMalloc system. These are analogous to DLmalloc chunks, except that regions do not carry any metadata at all. The run stores the metadata for all of its regions in the chunks header. The region address is the return value from a malloc call and should be the argument to a free. JMalloc is at its core a bucket allocator. Each arena has a set of logical bins, each of which services a specific size class. Allocations are made from the bin with the smallest size large enough to fit the allocation request. On Android, there are 39 bins. By having a carefully selected and limited list of bin sizes with small steps between them, fragmentation can be decreased. Note that on DLmalloc, bins are only used as free lists. On JMalloc, bins are used for all allocations. Bin metadata is stored in the arena structure. Each run is associated with a specific bin, and each bin has a current run which points to the non-full run from which it is currently allocating. Here you can see the 39 bins for the first arena with their metadata addresses, size classes, and current run pointers. If a run becomes full during an allocation, JMalloc will check if there are any non-full runs for this bin in the arena. If more than one non-full run exists, the one with the lowest address will be selected and set as the current run. If no non-full runs are available in this bin, a new run will be created in either an existing chunk or in a new chunk, and that run will be set as the current run of the bin. Arenas keep track of their non-full runs in available chunk space using a set of red-black trees. Finding a non-full run or available space for a new run is thus at most an O log n operation. JMalloc reduces lock contention in a few ways, thereby improving multi-threaded performance. Firstly, each arena has its own locks, so operations on different arenas do not contend for locks. Secondly, the critical time is very short. The lock only needs to be held when allocating new runs to a given bin or when flipping the in-use bits of a region in a run. These mechanisms already make jmalloc significantly more multi-threaded friendly than dlmalloc. However, Jason didn't stop there. He also implements something called thread-specific caches. For each thread, for each bin, there is a T-cache. The T-cache is a list of recently freed regions for the specific bin and thread. When allocating, jmalloc first looks to see if there is a region in the T-cache for the required sizes bin before going to the current run for that run. If so, it uses that region. When freeing a region, jmalloc pushes the region onto the T-cache for the relevant bin. The T-cache is last in, first out. Regions which are currently held in T-caches do not have their in-use bits set to free. Instead, they are considered by the greater jmalloc system to be in use. This saves on locks, as it's only necessary to grab a lock when updating global data structures, such as the run headers. Thread-specific data structures are by definition safe from other threads, and thus in many cases jmalloc allocations will not grab any locks at all. If jmalloc tries to allocate a region for a given size and the thread's T-cache for that bin size is empty, a prefill event will occur. When prefilling, jmalloc will lock the arena, mutex, allocate a number of regions for this bin from the current run, marking their bits in the run bits map as in use, push these regions onto the thread's T-cache, and then release the lock. This ensures that there are always a same number of regions in a T-cache and significantly improves locality, as a given thread will allocate regions of the same size from mostly contiguous memory. Each T-cache has a maximum number of regions which it can contain. For small bins, this is 8, and for larger bins, this is 20. When we reach this maximum, a flush event occurs. At a flush event, jmalloc takes the oldest half of the T-cache, these regions, and really frees them, i.e. it grabs the lock and marks the region's bits as free. At this point, they are free to be allocated by other threads. In addition, jmalloc implements a garbage collection mechanism. Essentially, jmalloc counts each allocation and free event. When this counter reaches a certain threshold, a so-called hard event occurs. Each hard event, jmalloc looks at a specific bin across all threads and clears out 3/4 of the regions from the T-cache for that bin. Again, the oldest 3/4 of the regions. During the next hard event, the next bin size will be targeted for cleanup. This is another way that regions can be removed from T-caches and returned to general availability. So when allocating on jmalloc, we observe the following flow. We first calculate the bin size for our request size. We then look in the T-cache of the current thread for the calculated bin. If the T-cache is empty, we prefill from the bin's current run. When the current run is exhausted, we prefill from the non-full run with the lowest address. If there is not enough regions in the existing non-full runs, a new run will be allocated in a chunk which has available space. If no space is available in a chunk, a new chunk is allocated from the system, and then a new run is allocated in that chunk and is used to prefill the T-cache. So now we've covered the essential details of jmalloc as well. Let's look at a comparison between the important properties of dlmalloc and jmalloc. dlmalloc is a best fit allocator, while jmalloc is a bucket allocator. dlmalloc uses inline metadata. User allocations on dlmalloc are called chunks. In jmalloc, they're called regions. dlmalloc allocates variable size segments from the system, while allocations on gmalloc from the system are always of fixed size chunks. jmalloc always allocates from fixed size regions. dlmalloc chunks can be arbitrary 8-byte aligned sizes. In dlmalloc, adjacent allocations are usually not the same size. In jmalloc, they are. dlmalloc has only the big lock, where jmalloc has fine-grained mutexes which reduce lock contention. jmalloc has thread-specific free lists, aka T-caches, to further increase multi-threading performance. jmalloc has a garbage collection mechanism which helps to clean up T-caches. And recently freed chunks or regions on dlmalloc are reused in a first-in, first-out fashion, while in jmalloc they are reused in a last-in, first-out fashion. In our estimation and what we see in the field, we believe that the current distribution of devices is roughly 70% jmalloc and 30% dlmalloc. This is largely due to the fact that most people update their phones relatively frequently, skewing the distribution towards the more modern jmalloc-based systems. Even though the bulk of devices are on jmalloc, and that will continue to be the case and will continue to be more and more true as time goes on, it's still necessary to exploit dlmalloc devices in order to get good real-world coverage. For example, certain geographical regions are more likely to have older phones and dlmalloc-based phones than other regions. Let's talk a bit about exploitation. Now that we know how the Android libc allocators work, we can try to determine what we need to do in order to exploit a heap memory corruption or a use after free. Exploiting these kinds of bugs is all about positioning, precise positioning of heap objects. We want to force certain objects to be allocated in specific locations in the heap in order to form useful adjacencies for memory corruptions or reuse of a desired location for a use after free. The operations performed in order to force the allocator to allocate the objects we want in the positions we want is known as heap shaping or heap feng shui. We essentially need to take advantage of our understanding of the inner workings of the allocator in order to allocate desired objects in the locations or with the adjacencies that we require. One of the things that can really make a huge difference when implementing a heap shaping for an exploit is having a way to visualize the heap, to see the various allocations within the context of the heap, the whole heap. For this we need tools. These tools need not be especially complicated or complex. We don't really need fancy GUIs to visualize regions or chunks. A simple tool which will allow us to inspect the heap state for a target process during exploit development will make an incredible difference. As it happens, ArgP and VATS presented a tool for visualizing the jmalloc heap at last year's INFILTRATE. They later released the tool, which they call Shadow, on GitHub with support for both Firefox's standalone jmalloc and Android's libc jmalloc. I highly recommend viewing their talk and using their tool. Shadow is a debugger plugin which allows you to view the various jmalloc structures and data in a textual table format, and it really makes a big difference in understanding how the heap is behaving during exploit development. Now, despite the fact that it's more than 30 years old, we were unable to find a similar visualization tool for dlmalloc at the time that we were working on it, so we wrote one. Today we're releasing Shade, a dlmalloc visualization tool on GitHub. This tool has an interface very similar to that of Shadow. You can request information about a given chunk using its address. This tells you the size of the chunk, its status, and the segment to which it belongs. One useful command is dlaround, which can give you a picture of the chunks before and after your chunk using the dlaround command. This shows a table of chunks centered around your chunk, including their addresses, sizes, and statuses. So if you know that you have a target allocation that you want to see the adjacent regions of, you can use the dlaround command to see the chunks as they're represented in memory. Once you know a segment's base address, you can use the dlsegment command to view all the chunks in that segment. Shade currently works only in GDB with Android's libc dlmalloc in 32-bit ARM processors. This is mostly just because that's what we've needed it for. Pull requests are, of course, more than welcome. While preparing for this presentation, I found that the excellent NCC group released their own tool for visualizing dlmalloc heaps about 6 months ago. While I haven't used it extensively, it seems like a really great tool and should also be looked into. Let's get back to the exploitation. For the purposes of this discussion, let's assume that you have discovered a zero-day heap buffer overflow in application X, and now it's time to exploit it. Modern exploitation is hard. As we've heard from previous talks, people are doing 11 bug chains to get from their initial remote all the way through to full system control. The Android system is one of the most heavily hardened platforms out there. Android devices implement a whole host of mitigations to make exploiting vulnerabilities and gaining control of devices more difficult. Things like address space layout randomization, SE Linux, and process sandboxing are designed to make end-to-end exploitation as painful as possible. We can, however, overcome some of these mitigations by the generous application of persistence, creativity, and luck. We usually end up breaking the exploitation down into a few steps, each of which uses a gadget of some sort. Gadgets are specific exploitations of your vulnerability set to achieve one or more functionalities, which can be chained together to create an end-to-end exploit. We usually need one or more gadgets to actually gain something useful. The gadget might come from different ways of exploiting a single vulnerability, or from different vulnerabilities. We usually need a relative read or write gadget to overcome ASLR, followed by arbitrary read or writes or execute gadgets to gain code execution. Once we have code execution, we can try to escape sandboxing or to evade SE Linux. How do we go about creating a gadget from a heap buffer overflow? We use adjacency. What we want to do is position the object containing our overflowable buffer just before another object, which we'll call the gadget object. We need to be able to trigger operations on that gadget object, which will, for example, use a pointer inside the object's data structure to perform a read operation. We can then cause the overflow, overwriting the pointer in the gadget object's data structure with a pointer of our choice. We then trigger the read operation to read data at our desired pointer. Using adjacency, we have created an arbitrary read gadget. We can use similar techniques to create write and execute gadgets. The key is to have a useful operation, which we can repurpose as a gadget by modifying object data through our overflow, through our memory corruption. In order to achieve this adjacency, we need to shape the heap such that our exploitable object is allocated just before our gadget object. Note that on dlmalloc, the two objects can be of completely different sizes, as dlmalloc allows allocations of various sizes to be contiguous. For jmalloc, however, the overflow and gadget objects must be of the same size class so that they'll be allocated from the same bin in the same run. This can greatly increase the complexity of exploiting on jmalloc, as it is necessary to find gadget objects which not only provide useful functions, but which fit in the right bin. If you find an object which will work for jmalloc, it may work for dlmalloc too, but the reverse is not true. Not necessarily true. So how do we go about performing the shaping necessary to get our objects allocated as desired? Remember that our interface to the allocator is very simple. We essentially only have the allocate and free operations. We need to use those to perform our shaping. What we need are some useful allocation primitives. We need some way to cause the target application to perform allocations and frees. Usually we'll look for something discrete and some discrete, easily triggerable functionality in the application, such as processing a particular kind of network packet or usage of a particular kind of object which performs allocations or frees as a side effect of its normal operation. It's important that the primitive perform the allocation or free operation we want at the time we want it, so we can use it to gain control of the heap. A given exploitation might require more than one primitive. The ideal primitive will allow us to allocate an arbitrary size, fill it with attacker-controlled data, and free it at a later stage with another application trigger. Although the ideal primitive is the holy grail, we will often have to make do with lesser primitives, for example, a primitive which only allocates at a specific size, or one which allocates memory which we cannot reliably free at a later stage. Some of these primitives, these lesser primitives, are more useful on jmalloc, and some are more useful on dlmalloc. The primitives you'll find in your target app really depend on the specific details of the target app. They might be the result of sending certain types of packets to the target, performing operations in a scripting context such as JavaScript, or creating and free objects through higher level, more abstract operations. Finding good primitives is a bit of an art form. It's often necessary to reverse a lot of code before useful primitives can be found. So what should one look for in a primitive, or when looking for primitives? You can start by looking for raw mallocs. These are probably the simplest primitives, a function which performs a raw malloc either with a size you can control or with a fixed size can be a useful primitive. Sometimes the allocations will be for a multiple of a structure size, for example. Another good source of primitives are C++ classes, which are allocated with a new operator. In most cases, this new translates directly to a malloc for the size of the class. If you can easily trigger allocation and freeing of classes of interesting sizes, you have yourself an excellent allocation primitive. Note that these are also good candidates to be gadget objects, so they're doubly interesting. Reallocs can also be a good source of primitives. They are often used with zero-length arrays in C structures in order to create variable length contained arrays of sub-objects. Realloc is essentially the same as malloc for our purposes. If your target process uses C++ standard template library, a good place to look for allocation primitives is in standard vectors. The growth of these vectors causes a new behind the scenes, which is essentially just a malloc times the size of the vector type, template type. As the vector grows, it might fit into the size bin you are interested in. It may be necessary to add objects iteratively until the vector grows to the correct size. Standard string also uses malloc to allocate backing stores for the strings it contains. If you can allocate a standard string from a raw buffer, the size of which you control, you have an excellent primitive. Note, however, that standard strings are often passed by value, which causes their data to be copied into new allocations. This can be a source of allocation noise, which you might want to avoid. In general, it's necessary to think really creatively about the accessible operations in your target in order to find the allocation primitives that you need. Let's walk through an example exploitation with the notes on some issues you might encounter on each of the allocators. First, let's define our assumptions. Let's say we have discovered a buffer overflow in an object of size 4e0. We are able to overflow an arbitrary number of bytes with controlled data starting from the overflowable buffer. Let's also say that we've discovered a useful gadget object with size 450 hex. This means that this object will be in the same size class as the overflowable object. Let's also assume that we have discovered an allocation primitive which allows us to allocate at an arbitrary size. We've also got the ability to free any of these allocations at the time that we want with a different application trigger. Lastly, we have the ability to determine by performing a certain operation on the gadget object, we have the ability to determine whether or not it has been overflowed. Just to remind you, what we need to do is to cause the overflowable object to be allocated immediately before the gadget object using the allocation and free primitives to shape the heap. Now, these assumptions that we've made are good assumptions. Why? Without a gadget object in the same size class as the overflowable object, it is almost impossible to exploit a buffer overflow on jmalloc. Without any arbitrary size allocation primitive, it is very difficult to exploit on dmalloc. One technique for heap shaping that we found to be particularly successful is called the placeholder technique, or at least we call it the placeholder technique. The idea is simple. Using our arbitrary allocation primitive, we allocate a bunch of placeholder sets for our target objects at the sizes of those objects. Each set of placeholders has a placeholder for the overflowable object and a placeholder for the gadget object. We hope that at least one set of placeholders is allocated such that the overflowable placeholder is directly before the gadget placeholder. Next, we iterate over all of our placeholder sets, and for each set we free the gadget placeholders and cause a gadget object to be allocated instead. Hopefully this gadget object will fall into the freed placeholder slot. Freeing and then immediately allocating on the same either in dmalloc should give you the same region, the same chunk in dmalloc, whereas on jmalloc it really depends which thread is performing the allocation and free. Well, more on that in a moment. Once more, we iterate over each of our placeholder set, this time freeing the overflowable object, the overflowable placeholder, and allocating our overflowable object and performing the overflow. We can then activate the gadget for each instance of the gadget object and use the result to determine if we have overflowed this instance or not. Hopefully, at least one set of placeholders will have been turned into a working gadget. This idea is the basis for the placeholder heap shaping technique. This technique can be used on both jmalloc and dmalloc, but there are various things to look out for on each of these respective allocators. One thing that can really help increase the probability of that one or more placeholder sets will have contiguous overflowable and gadget objects is to spray a large number of allocations of the relevant size class at the very beginning of an exploit. This will hopefully cause any best fit chunks in the dmalloc free lists or partially used runs in the jmalloc bins to be used up, filling the holes. The placeholder allocations will then most likely be from new dmalloc segments or new jmalloc runs with successive allocations for the same size classes falling one after the other. One problem you may encounter is that the allocation of the overflowable object, the gadget object, or even the allocation primitives themselves performs more than just the target allocation, the one that you're interested in. In fact, it's very common for one or more of these to perform a bunch of smaller or bigger allocations around the actual target allocation we're interested in. These unwanted allocations shouldn't make any difference when using jmalloc, as we're only concerned with allocations in our bin size in jmalloc. On dealmalloc, however, these allocations might fall between the overflowable object and the gadget object, messing with our heap shaping. Assuming the gadget object is the one which allocates the unwanted allocations, one way to deal with this is to do the following. Firstly, at the beginning of the exploit, we allocate a bunch of smaller blocks, let's say 100 blocks of 100 hex bytes each. We then allocate all the placeholder sets. Then, for each placeholder set, we first free the gadget placeholder. Then we free a few of the smaller filter allocations. These will be added to the free lists, the free bins. Then we allocate the gadget itself. The smaller unwanted allocations will use the free filter allocations we just freed, and the gadget itself will fall on the region that we wanted to, the placeholder. On dealmalloc, freeing a placeholder can cause it to be consolidated with an adjacent free chunk, resulting in it being placed in a larger bin's free list, and it then might not be used for the next allocation of that placeholder size. In other words, the placeholder object will not be used to service the gadget or overflowable object allocation. We can solve this quite easily by using pinner allocations. The idea is that simply that you allocate objects before your first placeholder and after your last placeholder. You never free these objects. As these pinners are always in use, and as we only free one of these placeholders in a set at a given time, there will be no consolidation of placeholders, of regions. Once you finally get your objects to be one after the other, there's an additional gotcha on dealmalloc. The metadata for the gadget chunk will be between your overflowable object and the gadget data. You need to overwrite this metadata with the size of the first and second objects respectively, otherwise the allocator will fail when it comes to time to free your chunks. On jmalloc, the metadata is out of band, so this is not necessary. Another thing to watch out for is that your primitive candidates may cause allocations or frees on threads other than the one which allocates your overflowable and gadget objects. In fact, the overflowable and gadget objects might not be allocated on the same thread at all. So your placeholders might be allocated and freed by one thread, but the gadget or overflowable objects will be allocated on another. This shouldn't present any problem for dealmalloc, which doesn't know anything about threads, but can be a significant pain on jmalloc. The basic question is, how can we move an allocation from one thread's Tcache to another thread? One way to do this is by forcing flush events. We free our desired placeholder region, R15. We then free up to 20 more regions on that same thread. This will fill up the Tcache, resulting in a flush. The flush removes the oldest half of the Tcache and marks those regions as free, making them available to other threads. We then allocate on a desired thread to get the region we want with the object content that we desire. Note that the desired region might not be first in line on the thread which allocates the desired object. You might need to spray a bunch of allocations on that thread in order to achieve the free placeholder, to catch the free placeholder. Filling holes before allocating the placeholders can help prevent this issue. Getting this right is really complicated and is going to be very specific to your target, your vulnerability, and the gadgets and primitives that you find. One thing to remember is that on jmalloc, the regions for your overflowable and gadget objects will be of the same size, the maximum size of this particular bin. This might be larger than the objects themselves, so when you overflow from your overflowable buffer, you need to pad that overflow with the difference between the overflowable object size and the bin size before you overflow any gadget object data. On dealmalloc, the objects are directly after one another except for the metadata between them. On jmalloc, it's also possible that the threads that are involved in your exploitation are assigned to different arenas. This can be problematic if you need, for example, to allocate contiguous regions in different threads. Arena selection is supposed to use a round-robin approach, but in reality, it always allocates a new thread to the arena with the least number of threads assigned. If you can create and destroy threads somehow before your overflow, you can do the following. You can allocate a large number of threads, let's say about 30. Then you can, these 30 threads will be evenly distributed over the two arenas. You can then destroy every second thread that you created, leaving you with one arena with 15 threads and one arena with 0 threads, then your allocation and primitive threads will all be allocated from the arena that has 0 threads in it. That's about all I've got for you guys. I hope that I've given you a foundation and understanding how the Android libc allocators work, their details, and that you've heard some tips regarding how to successfully exploit or what problems you might encounter when trying to exploit vulnerabilities on Android as a result of these allocators. A write-up of this talk and other interesting technical content is coming soon to a blog near you. We're opening up a blog, and hopefully there will be a lot of technical content, especially including the write-up for this talk. So please check it out in the future. Feel free to approach me during the conference or to contact me via Twitter or email with any questions you might have. I'm always available to and always happy to help people understand the complex world of exploitation and real-world exploitation.
All right, I have a question. Okay, so if you did the overflow from the overflowable with all 3 of them, like I think you demonstrated in your technique, is there not data in between the overflowable and the gadget potentially that you're corrupting that would then cause instability?
There is definitely a possibility of overflowing for any random object generally, okay? And that's definitely a problem that you will encounter where you might overflow some random object which then it tries to use something and dies. There are techniques that you can use to try to avoid that. Like I said, one of the techniques is to try and get as many placeholder sets to be aligned one after the other. Okay, is using the pre-allocation of a large number of filling holes, using allocation of a large number of structures of the size class of your primitives, of your objects. There are a bunch of more techniques that we've developed over the exploitations that we've done, which have helped us get to 99% stability on these exploits, even though theoretically there could be places where things might go haywire here.
Okay, you heard it here first. 99% is good enough.
Yeah, we aim for more, but yeah.
All right. Who wants a shirt and has a question that is at least that technical? There's someone over there.
Someone over there?
Yeah. I can just barely see the light.
Yeah, I know the light's too shiny.
All right, here we go.
Hey, so I've done a little bit of Android exploitation, and I noticed this DL malloc, J malloc issue between a couple of the handsets I was testing on. And at the time I was like, oh, well, whatever, I'm not really interested in the old devices. But I was curious, have you found any techniques for writing, like, because the question I was looking at a one-shot exploit at the time, and I thought, you know, if I actually wanted to make this work, like, for real on lots of devices, I would have to have an exploit that wouldn't crash on DL malloc and would work on J malloc or vice versa.
So are you asking if it's possible to create a unified DL malloc, J malloc exploit?
Yeah, exactly.
So the short answer is maybe, and the large answer is yes. It's possible. It's possible. It's very difficult and really depends on your gadgets, your primitives, what you have to work with in the process. It is possible though, and with enough dedication and luck, you might be able to do it. We have done this in the past, but it really depends on what your primitives are, what you have that you can use to do this.
With the placeholder technique, any preferences on doing all of the overflows at the same time or checking in between?
It really depends on how you're able to detect whether your object has been overflowed or not. If you're able to check, obviously time is money, and especially when you're talking about remote code execution exploits on Android devices. If you're exploiting the browser, you want your exploit to be as quick and as fast as possible so that people aren't left with hanging pages or whatever for 30 seconds. So time is really an important factor. So if you're able to detect your overflow sooner because you've landed on a placeholder set that is good earlier than before, you can reduce time. And so it really depends on what your trade-off is. In many cases, we've tried to determine immediately whether we've been overflowed, and it also reduces the possibility that you spray something and hit something random, which then dies and will kill your process. So it depends on how you can get that earliest possible information that you've managed to overflow and you've managed to do your heap shaping correctly. Hope I've answered the question.
Thank you so much.